Good afternoon, everyone. We are live from Melbourne. This is the Future of Data Meetup that Hortonworks and Cloudera used to run a few years back. And we are so excited, and it's been a long time coming in starting this once again. My name is Saurabh, and today's topic we are so excited to share with you about real-time streaming data, Apache Flink, how we do SQL on top of Flink, and we have a superb speaker along with myself who will talk about these topics today. So, super excited to get this started. I'll be the host for these talks going forward. My name is Saurabh. I'm based in Melbourne. And I'm part of the solutions engineering team based in Cloudera. Part of the Melbourne team here. And prior to this, I was part of the solutions engineering team in Hortonworks, based in Singapore. So a quick agenda for today's talk is basically we start off the meetup, and I'm so happy again, and thank you once again for everyone who joined today's call. We also have a great team of social media experts behind the scenes, Frila and Ramon. Thank you so much for making this happen. Going forward as well, they'll be helping us broadcast live onto YouTube and LinkedIn as well. We'll start off with an introduction on the technology and the Apache technologies that we want to cover off today, which is basically Apache Flink. We'll talk about how we do SQL and SQL on top of that. We'll also have some time for demos and also take some questions later on. Yep. So a quick thing on the logistics is we also have some nice swags to give away at the end of this. One small thing that you need to do is basically stick around till the end of the talk and ask some great questions. So the speaker and I will just pick the top 3 questions, and we will decide who the winner is and post these awesome swags to your personal address. And the speaker for today is my great friend and colleague, Andre. And we've worked on numerous projects together, and Andre is such a great speaker and a great inspiration for me as well, because he's so knowledgeable on the streaming side of things. And I'm so happy that he's here to educate us on data in motion, Apache Flink, and stuff like that. So it's great to have him over here, and I'm sure later on in the future talks as well, he'll be happy to share other technologies as well. So Andre, how are you doing today? And over to you as well.
Thank you, Saurabh. Thank you very much for the introduction. Yeah, so my name is Andre Araujo. I'm a field specialist at Cloudera, and I specialize on the data motion products that we have in our stack, namely Flink, Kafka, and NiFi. I actually joined Cloudera on the 29th of September 7 years ago to this day. So today I turned 7 in Cloudera. It's my 7th anniversary. I joined the company as a solutions architect in the professional services team, and only about 2 years ago that I moved into this role. Cool. So let's go into the topic for today. So before we start, I just wanted to do a quick overview of what Flink is. I don't know within the audience, among the audience, how many people know Flink. So I won't assume that all of you know what Flink is. So I want to quickly cover Flink. We're not going to go deep, but so that you know what we are talking about in here. So Flink is another distributed data processing framework. It gives us an API that allows us to build streaming pipelines and event-driven applications, which are applications that can process events in real time or near real time. These applications run in a distributed engine, a distributed framework, and they can scale to very large volumes of data being processed in near real time with very low latency by the framework. The if you're familiar with Spark Streaming or Kafka Streams, Flink is not much different in the sense that it's a framework to process event-driven or events or real-time events. What makes Flink different is the features that the framework has that makes it very flexible and highly scalable, being able to handle messages with very, very low latency and being able to scale to very high volumes of messages to process. Differently from other systems like Spark Streaming, which was born as a batch processing framework and then later was adapted to process data in a streaming fashion, Flink was built from the ground up with a streaming use case in mind. So when and it was optimized, and everything that was done in Flink was with that use case in mind, so that we could process data with very low latency and very efficiently. So when a Flink application looks at a data stream, real-time data streaming through, it looks at that as an unbounded stream abstraction, just as a string of events that come one after the other and never end, right? They come forever. So you can, on top of that, you can define your operations, your transformations, your calculations, and when you run your job, the job will process that stream of events and continuously apply those operations and calculations until the end of the days or until you stop your job. The good thing is that the same analogy and the same abstraction was also used to process data in a batch way, in a batch-driven way. So when we need to process batch type of processing in Flink, we can also look at the data that you're going to process as a stream of data. But now, instead of that stream being unbounded, Flink gives us a way to define logical boundaries in that stream. And that logical boundary allows us to logically group events in groups or in batches, and that which provides us the ability to produce results in a batch-oriented way. The strings of events are still processed by the same engine as if we were processing streaming events, but we are able to distinguish and process batches in that data separately. And this abstraction serves most of the use cases, streaming or batch use cases that we might want to process with Flink, including data pipelines, doing transformations on the data, doing analytics, complex event processing, and the implementation of event-driven applications. When we look at an application that's processing events or a stream of events, we usually, as we process events, we want to keep context of what has been processed so far. So for example, if we are computing a running average of a certain metric that comes in events that we receive in real time, we want to keep in memory some counters or some assistant auxiliary variables to keep some intermediate computations. So for a running average, we need to keep at least like a count of the number of events that we receive so far and the sum of those metrics so that we can divide those and calculate the running average. So once we receive one message, we need to have that computation already calculated for all the previous events, and we usually keep that in memory, and it's what we call the state. It's the context of that calculation. And as we receive events, we update that state and we produce the output, which is the running average for that application. In a traditional application, that state is usually kept in memory, but eventually we want to offload that to disk or to some kind of storage, because like we might have to store a lot of data in memory and there might not be room for that. And in traditional applications, the choice for that storage is usually an external database or key value store where we can put that value in. This works well, but it has the disadvantage that you have all the network round trip between the application and that store to record to save the value. which can affect the throughput of the application. In Flink, this is done differently. Flink has a state management feature, which is a first-class feature of the framework that helps you keep track of those intermediate computations or that state in a very easy way without you having to actually implement that yourself in your application. The state is stored locally, so that once you receive events and you need to process events and need to access that state, you don't need to incur in extra network round trips or delays to do that. So everything happens very fast, and it's managed by Flink within the framework, and without you, more importantly, having to implement anything special to do that. This state, as I mentioned, is stored locally on the machines. It's distributed across all the executors or all the parallel threads that are processing your application or your job. Flink can store that in memory or in disk or a combination of both. And on a regular basis, it takes snapshots or checkpoints of that state and store that in the durable storage somewhere else, so that if your application stops or it crashes, it can actually recover and continue to process data from where it was from where it stopped before, without having to rewind to the beginning of the days and reprocessing everything all over again. Right. So this gives you the ability to implement a lot of very complex different types of applications, which we won't have time to cover here today. The small application that you're seeing on the screen now, it's an application where you have a Flink application that processes transactions from a real-time source and computes balances for the accounts of a fictitious bank. And it also processes queries from other sources about those balances, and you can update the state as you compute the transaction balance. As you process the transactions and update the balances, these balances are kept in the state, and you keep that in state. And the queries can come to ask for a particular balance or an account, and this same application can process these dynamic queries and serving the result from the state. I'm not going to cover exactly this implementation here, but this implementation is part of a tutorial that we have available in our GitHub. So if you're interested in knowing more and actually walking through the implementation of this, you can find more information about this in the GitHub address that you have on the screen. So state gives you a lot of goodness in terms of keeping and keeping intermediate information within your application and speeding up processing for your application, as I mentioned before. But it also gives you a lot of other good things in Flink that comes from the ability of having state and being able to manage the state efficiently. So, for example, with state management built-in in Flink, you're able to actually stop and resume your applications without losing the exact point in time where you're processing your messages. So you can, if your application needs to perform exactly once delivery, you can stop and restart application without compromising that. You can query the state of your application from within and also from the outside of your application. So Flink gives you an API, a REST API, that allows external applications to tap into and do lookups against the state of your application. If your application is evolving, the state can also evolve with the application. So you can, for example, create a new version of the application, and you stop your current version by saving the state, and then you can resume the new version from the same point where the old version was without losing any processing or any data in that process. So there is a lot that you can do with state. It's as I said, it's an integral part and a first-class feature of Flink, and it makes it really robust and efficient to process data at scale. So one question that we get a lot is, okay, so we already have Spark Stream and Kafka Streams, so why do we need Flink, right? And by the way, Cloudera actually supports those three processing engines: Spark Stream, Kafka Streams, and Flink. So if you're using CDP, the Cloudera data platform, you have the option to do those three. But why the three of them? Well, it comes down to a lot of different factors, right? So one of the factors that counts a lot is like familiarity. Like if you have a team that are experts in Spark streaming and they want to do streaming, like the most natural thing, unless there is something that Spark streaming cannot do, is for them to continue to use Spark streaming. The same thing with Kafka and Flink, right? So if you already have, if your teams, your development teams already gravitate towards any one of these technologies, unless there is a really good reason, like you shouldn't be changing that straight away, right? But each one of these also have pros and cons and have things that they do better than the others. So depending on what you're trying to achieve, and if you're starting from a clean slate, it might be better to pick one over the other. As I mentioned, Spark streaming started as a streaming process, a batch processing framework, and it's very good at doing that. It can process a very large amount of data with very high throughput. Later, it was adapted to do streaming processing, as in Spark streaming. And it's also very good at that, but it doesn't process events individually in a streaming first fashion, right? So it's based on the concept of micro batches. So even though it can achieve high throughputs and relatively low latencies, it cannot go to latencies as low as Flink and Kafka Streams could do, for example. It also doesn't have the same state management features, for example, that Flink has. So if you need low latency and state management, you should be looking for other frameworks. On the other hand, like Kafka Streams, is implemented. It's part of the Apache Kafka project, so it has a very good affinity with Kafka. So if your applications, your streaming applications, they read data from Kafka and write data to Kafka, and they don't do anything else, Kafka Streams can probably simplify what you need to implement. So that could be a good option if that's the case. For everything else, I would say if you need more flexibility, if you need low latency, if your application needs state management and being able to scale that state to very large sizes, Flink is the best option here. It gives you a lot of tools, a lot of different options in the API to implement jobs that do exactly that without you having to spend a lot of time working out the details. If you need to know more about this, or if you want to know more about this, we have a white paper on our website that compares those three technologies and give you an idea of when you should choose each one of those, what they're good for, what the pros and cons for each one of those. Okay. I just listed here a couple of use cases that we have been working with customers without naming names. I'll run quickly through them because I want to spend more time on the actual product and technology. But we're doing some work with a telco in Germany on the cybersecurity space. They want to do intrusion detection at near real time. Like if you're trying to detect that someone hacked your network, that information is only good if you can do that very quickly. If you take like hours to figure out that someone hacked your network, by the time you know, the damage was already done. So Flink is really good at processing the like the variety of different types of information that we need to process to come to those decisions in a very, very quick and scalable way. We also working with a bank in the US to do analytics on user transactions so that we can calculate the cost of each transaction and offer each one of the customers personalized products for their consumer profile. And Flink can also do this at very high scales and very reliably. We can implement exactly once processing guarantees in Flink jobs, which is very important when you're dealing with very sensitive financial transactions where you cannot miss or process anything in duplication. And also international telco company that we've been working on to create models to help detect failures and events in their network so that they can react to that as quickly as possible and improve customer satisfaction by reducing the amount and the duration of outages in the network. Okay, so
I'm back again. So I had a quick question,
thanks,
Andre, on this. So thanks for the overview and the use cases. I have worked personally on a number of different streaming engines myself, for example, Apache Storm and some of the others. Just curious to know, right, how easy does Apache Flink make it for existing data engineers or analysts to interact with the system, and what's the learning curve like for these kind of people?
Good question. Thank you, Sarab. Yeah, that's a great question. And it's a good, actually, segue for what we're going to talk about next. So when you start working with Flink, Flink offers you 3 main APIs to implement your jobs within the framework. Right. So, and these APIs give you different levels of conciseness and expressiveness so that you can pick and choose the one that suits you the most and makes it easier or more complete to implement what you need to do. So the lowest level API is called the Process Functions API. It gives you all the control and all the whistles and bells that you need to implement anything that you want to do in Flink. Right, so you have a lot of control. You can tweak the way Flink works here to suit exactly what you need to do. One of the cons of this using this API is that it's a more prolix API. You have to write more code and you have to take care of more things yourself. But on the other hand, it gives you a lot of control and you can extract from Flink everything that it can offer, right? If you want to go a little bit high level than this, the next API is the Data Stream API. And with the Data Stream API, you already get a lot of abstractions that let you create your flows, create your transformations without spending too much time worrying about all the nitty-gritty details of a Flink process. Right. So in the Data Stream API, the programs are composed of logical data flows. So you create your logical flows and you implement them in your job. And these flows are basically a DAG, direct acyclic graph, comprised of operations and transformations between them. Right. So it's a sequence of transformations that will implement what you want to achieve. So for example, this is an example of what a word count or a click count would look like in the Data Stream API. You start with a stream of events that you're reading from somewhere, let's say Kafka, and then you apply transformations to that stream of events. So here we are mapping each event to tuple with the click, the user ID, and a count here of one event. And then I can key by the user ID, aggregate in a window of 30 minutes, and then calculate a sum of all the clicks for that particular user ID, right? So the output of this pipeline is going to be an aggregation over windows of 30 minutes of how many clicks each user performed within that window, right? So this is higher level than you would do with the process function. It allows you to focus on the business logic, and Flink will take care of translate this into an execution plan for running this job. If this is too low level for you, like you have the next option, which is the higher level API that Flink has at the moment, which is the SQL and Table API. And with the SQL and Table API, you can actually, instead of writing a data flow program as we had in the previous slide, you can just write a SQL query that does the same thing. So here I'm counting the number of clicks per user ID for a window of 30 minutes from my string of clicks, right? So this does virtually the same thing that my previous slide used to do, but for a lot of people and for a lot of especially analysts that don't know how to code in Java, this is a lot easier to do than writing Java code. The good thing is that the SQL and Table API, they work as well on stream as on batch. So you can actually run the same query against a streaming source and a batch source and have similar results. The SQL that Flink uses is based on Apache Calcite, which is 100% ANSI compatible. So you don't need to learn, if you're familiar with ANSI SQL, you don't need to learn new dialects of SQL to use this. The SQL that Flink uses should be already familiar to you. Okay.
Yeah, that's superb, Andre. So, quick question on this, right? So we're talking about SQL on Flink. I think it's one of the most powerful capabilities, and working with so many different streaming engines, SQL has always been a problem, and it's very familiar for data analysts coming from a warehouse or an Oracle background, adopting a streaming engine and then writing SQL on top of that. So it's quite powerful. So in terms of this and the ecosystem around Flink, can we talk a little bit about what SQL Stream Builder is all about and what's its capabilities and things?
Yep, absolutely. So as I said, the SQL and Table API makes it a lot easier for users to define a logic to apply to a string of events or to perform a transformation on a stream of events. But bear in mind that this is still an API that you need to use within your Java application, your Flink job, right? So you would write your job in Java using the API, and you would actually embed this SQL somewhere within your job so that your job can actually execute this SQL. So even though this makes it a little bit higher level, it still requires a Java developer to create that job and like embed this in there for you. Like, so it's not as accessible to a business analyst that doesn't know how to program in Java as we would like it to be, right? And that brings us to talking about the SQL Stream Builder, which is the main reason for the topic tonight, which is how we make this more accessible to people who don't know Java, right? So to the masses, to business analysts, or to other folks who don't know how to create a Java program. So SQL Stream Builder is a product that was created by a company called Eventador, and Cloudera acquired Eventador sometime last year, and we've been investing on the technology to complement Flink on the Cloudera data platform since then. So what SQL Stream Builder gives us is a service or a tool that allows you to gives you a console where you can go and write your SQL query. You can see the tables that are available to you, write your queries to query the data or transform the data and write the data to other places, and run that without having to write a single line of Java code, right? So behind the scenes, when you press execute, as we're going to see in a few minutes, it actually converts that SQL into a Flink job that's going to run in your production Flink deployment with all the high availability and fault tolerance that it can have in a Flink execution. But you don't need to worry about that. Everything is taken care of by SQL Stream Builder for you without you having to write that SQL code. So what it gives us, it's a continuous SQL engine that allows us to create these streaming SQL queries that run continuously, reading data from either high-velocity sources like Kafka, but also from batch sources like relational databases, and processing that data and sending that data to other places. And those places could be, again, Kafka, if we need that data to be processed downstream by some other applications. It could be saving that data to data stores or databases, to file systems, to places like S3 and Amazon, etc. Right? And all of this can be done without having, again, to write Java code. So in SQL Stream Builder, so since it's based in Flink, it gives you the ability to process string data as well batch, but more importantly, and which makes it very powerful, is it unifies, it's able to unify those two things. You can actually have a table that's mapped to a Kafka source, and another table that's mapped to a database or a Hive table, and you can actually join those tables and merge the data that's coming from those two sources together to do what you need to do in your processing, to enrich data, to calculate aggregations, etc. So this is very powerful, and it already comes with a number of connectors and sources and sinks that allows you to interact with a variety of different sources and sinks there, like Hive could do databases that provide JDBC support, like Postgres, MySQL, and others soon to come. So some of the features of SQL Stream Builder, it supports, it has supports for Flink Catalogs. So the Flink framework, the Flink API has support to catalogs where you can plug catalogs from other systems like Hive could do. And when you do that, you can actually reference tables, Hive tables, or Kudu tables directly from your Flink jobs. So the same support exists on SSB, so you can easily access those sources without having to do a lot of work. You can create and define tables using DDL connectors. So you have a lot of different templates for different types of DDL, a lot of DDL templates to create different types of tables. So if you want to create a table that connects to HBase or Kudu or Oracle or MySQL, all those templates are made readily available for you in the console as well. And as I mentioned before, like you can process streaming along with data that's stored at rest for batch processing in the same query, so that you can use like data from a database or a database table to enrich the streaming data that you're processing at the moment, or vice versa. So this is an example of a query that you could write in SQL Stream Builder. And again, there is no Java here, it's only pure SQL. So here we're getting events from trucks that are running around the country, and we have two string of events. One string that gives us the location of the trucks, and another string that comes from the speed sensor on the trucks that gives us the speed that those trucks are traveling on. And I want to join those to know where the truck is and what speed the truck has at any point in time. So I can join those as if they were two tables here. And then I join, I have a Hive table that has the employees, the list of employees with their employees ID. So I want to know who is the driver for each truck. So I can use this information that's coming from Hive table to enrich the information that I have streaming through my Kafka topics. And then I join that information with another table, but this table in this case is stored in a Kudu database that have what I'm looking for here. Yeah, so I just want to enrich that information with some other column that I have in the Kudu table, and this is just to show you that like there is no, I don't have any limitation here. I can have two topics being joined in the same query as a Hive table and a Kudu table, so that I can produce the data that I need to calculate. And then on top of that, I can apply transformations, aggregations. Flink and SSP gives us support to many different types of windows. You can have tumbling windows, sliding windows, count windows, so that I can compute the aggregations that I need to compute.
Yeah, Andre, so this is quite powerful, right? So what you're doing over here is you are processing the streaming data coming from Kafka and joining that along with batch processing systems like Hive and Kudu, and possibly even HDFS. So that's quite powerful. And I was just quickly taking a look at the questions that were coming in on YouTube as well as LinkedIn, and some really good questions, right? Do you mind we start answering some of those? Possibly links back into some of the things that you're talking about?
Yeah. Let's take one question, because I want to move quick, because I don't want to miss the demo, and then we'll move to the demo.
Sure. So let me take something which is very similar to what you're talking about currently. So the first question is from Sharon Matthew on LinkedIn, and he asks whether we can do batch processing with Flink.
Yes, we can. So we currently support batch processing in Flink using the SQL and Table API. As I mentioned, the SQL and Table, the queries that you specify in the SQL and Table API, they can be applied both to streaming sources and batch sources. And we currently fully support batch processing using that API. So if you have a source of data that's coming from HDFS, for example, or from a Kudu table, you can actually create a job using the table, the Flink SQL and Table API to process data in batch, and it's fully supported.
Cool. Just one more before we move on, Andre.
Sure. Yeah.
So can we? This is from Ananya on LinkedIn, and she asked whether we can do Python, Java, R on Flink.
Good question. So currently, the mature APIs that are available with Flink are Java and Scala. So those are the two APIs that we support at the moment. If you look at the Flink Apache website, you're going to see that there is also a Python API that's in the works. That API is the less mature of the three, and for that reason, like Cloudera doesn't fully support it yet. But I think it's just a matter of time until like the community embraces and matures and make sure that the API is solid, and then we'll start supporting it. But if you want to play with it, like it's already available there, but it's not a production grade API yet.
Cool. So keeping the time in mind as well, let's do maybe 10 or 12 minutes of the demo before we move on to the rest of the questions, because Because there are so many different
So I
questions.
skipped some slides here, and I'll cover these in the demo anyway, so I'll jump straight into the demo. So what you're going to see in the demo is just a mix of all of those things that we talked about. So I have a small application that gets CPU usage, temperature, and battery consumption from machines, in the case, my laptop, and streams that information into a Kafka topic, right? And then I'm going to use SQL Stream Builder, which has Flink underneath, to process that data and do analytics with that. I have some data that I have stored, some reference data, lookup data that I have stored and could do, and I want to use that to enrich my my stream of data. And once I process the data, I want to produce that data to different places. I want to send some of that data to Kafka so that other applications can start reading the enriched data that I produced. Some of the information I want to put in Caduce so that I can feed BI applications from that. And SQL Stream Builder also has a concept of a materialized view, which is like a materialized view that you can define on top of streaming data that provides a snapshot of that data that's flowing through the stream available through a REST endpoint. So if you have other applications or dashboards that can read data or pull the data from those REST endpoints, that becomes readily available to you. So let's jump into that, and let me. So what I have here is the SQL Stream Builder console, right? So it's just a console where you can jump on and start writing your own SQL here to process the data. You can define tables, and when you define those tables, you have different options of tables that you can create. The most straightforward one are Kafka tables, which are tables that are backed by a Kafka topic, right? So as I said, let's make sure that my application is generating data. I have data from my laptop being streamed into my Kafka cluster. So if I look in my Kafka cluster for those topics, I can see topics here that have some data. I have data about all the tasks that are running on my computer at this point in time, battery consumption, and temperature. If I look in here, I can actually see I have a sneak peek of what type of data I have there. I have a timestamp, the name of my computer, PID, what task it is, Google Chrome, how much CPU it's being used, etc. Right? And I want to process this in some way. So if I go to SQL Stream Builder, the first thing that I need to do is just to map a logical table to that topic, so I can start writing SQL against that table. So I could just do like tasks name for my table, and then I can pick. Oh, I think I need to log in again. Okay. So go to tables, add table. So I create the tasks table, choose my Kafka cluster, pick my topic, perf tasks, and then I can specify a schema. If I don't know the schema, I can tell it to detect the schema for me, and it will look at the data that's flowing at the topic right now and tell me what the schema that is. I can specify which column represents my event time for that particular event. I can specify transformations if I want to cleanse some, like convert hostname to lowercase or things like that. So, and then once you save changes, it will create that table for you. I have already created those tables in advance. So I have the 3 tables here that map to those topics. So if I want to start querying this, for me, it's very simple. It's just simple SQL. I write a SQL. So here I'm not doing any aggregation. I just want to see what data is flowing there and if the data is actually flowing through my topics. So it's launching my job here, and it should start showing me samples of the data on my screen. Yeah, so I see the data here. I actually have a lot more data, but the console doesn't show 100% of the data here. It just takes samples every second and show me a sneak peek of what's flowing through there at the moment. But here I can see the different tasks and CPU measurements that are flowing through there. So that's good. We know that this is working. So let's do something a little bit more interesting with that. So for example, I want to calculate, and I have some, I want to calculate some running CPU usage per task or per type of task, right? So here I can, for each process name, I want to calculate the sum of CPU used by that process in an incremental way. So this will give me a running average or a running sum of milliseconds that the process spent in CPU. So if I'm running this, oops. No, I had something selected. Yeah, I had selected something and pressed execute and was trying to execute just part of that text. So if I run this, now I'm doing some aggregations now. So I'm calculating for each process name how much CPU the process used up to that point in time, right? So here I can see on the screen, but what if we want to use this information to do something more interesting, right? So I'd like to write this somewhere else that I can use in a downstream application. Yeah, so let's say I have a table in Kudu, and I already created some table here, and I created a table to hold cumulative information for those tasks, CPU usage. So I want to write the data into that table, right? So in SQL, it's very simple to do this. It's just to insert into that table, and the column names that I have there are PS, timestamp, task, count, and CPU milliseconds. Right, so as I execute this, my job is going to run exactly as it was running before, and it will actually show me the output, the samples on the screen here, so I know that it's working. But now if I go to my Kudu cluster here, and I select from my task cumulative.
Could you zoom into your screen a little bit?
Yes.
Yeah, that looks
better.
Yeah.
Yeah. So if I run this query in Kudu, now I can see that not only I'm seeing the output here on the SQL Stream Builder console, but I also now have the data being updated in Kudu straight away in real time, right? So I can, I'm running a job here, and I can see my jobs running on my SQL Stream Builder console. If I go back to the console and clear my screen, like the job is still running there on the background on my Flink cluster, and I could go here and write other jobs, right? So just for the sake of speed here, let me write another query. So this is a similar query as the one before, but instead of aggregating by task, now I'm aggregating by host name. So I'm calculating the amount of CPU that each host is using on a cumulative way. But more than this, now I have another table that is in Kudu that has batch data there with metadata about my machine. So I have my machine, IP address, and geographical coordinates for that machine, for example. So what I'm doing here is I'm joining my stream of data that's coming through this perf tasks table, joining with my Kudu table that has the machine metadata, and enriching my stream of data with the latitude and longitude of that particular host name. And the results here, I'm writing again to a Kudu table so that I can have that and use that in other applications, right? So if I run this, oops, same thing, I had selected something. So I'm running this, and we should see data coming through. Yeah, so data is coming through now, and it's going to my to-do table. So I could, for example, now, if I go to the Cloudera data viz apps, I can create dashboards here to read from my to-do table, right? So here, for example, this is reading in real time from those tables that I'm writing in to-do. So I have the breakdown of, and you can see that it's actually updating here as we speak. It updates every 5 seconds, so it's moving data. And I have a breakdown here of what are the tasks in my notebook that consume more CPU. The top one here is Google Chrome, followed by Docker. So those are things that I'm heavily using here. I have the geolocation here showing me that my computer is somewhere in Australia, and also some other charts there. So this is just a quick example of what you can do with this. You can quickly process data, streaming data in a scalable fashion, write that data to locations like to Kudu or to other databases where you can take advantage of that for other applications later on, right? So let's jump back here and let me stop this because my cluster is just a small cluster. I don't want to flood it with things. And let's create a new job. So there are the things you can do with SSB, with SQL and Flink, right? So all the queries that we did now, we did group bys, but we're just doing a running count or running sum of data. I didn't define windows. And the streaming SQL syntax that you have in Flink allows you to define different types of windows. So you can define those windows and create computations within those windows. So here, for example, I'm creating a tumbling window on my perf tasks topic, and calculating aggregations every 10 seconds. So for every 10 seconds, I calculate how much CPU was used at my host name. So what was the CPU utilization in 10 seconds interval there, right? I can, in the same way that you create views on relational databases, I can create views in here. So I can create a CPU usage view as this. Oops, I think I already had that created. Drop view. Okay, so I created the view, so I can now, for example, do a select from CPU usage, and that will give me the computation performed by that view, which is computing the CPU usage for my computer in intervals of 10 seconds, right? So let's wait just a couple of seconds. Yeah, and now we have this here. So said, like, I'm generating this data. Let's say that I have applications that want to make use of this. So I might want to write that to a topic back in Kafka so it's available for the other application. No problem. I have a query here. And if I want to insert that into another Kafka topic, I have a number of different templates here. So let's say I want to write to Kafka as JSON. It will generate a template with a create table for me that gives me like CPU usage, CPU summary. So I'm going to create a table here called CPU summary that's mapped to a Kafka topic that I'm going to name CPU summary. Right, so when I run this, I create a table in Flink. So now I have a table that I can write to. And now that I have a table, I can just go ahead and do an insert into CPU summary from this select here, right? So when I run this, I have my query running. And if I looked at my Kafka cluster now, should see my topic appearing here in a moment. Just see. Yeah, so the query is running. Yeah, and the topic will appear here at a moment, and we will see that it can it will have data in there. But just to finalize the demo here, I just want to show you a very nifty feature of SQL Stream Builder, which are the materialized views. So as I have a query running here, I want to maybe make this available to other applications through a REST API, right? So I have the ability to create a materialized view on top of this. I need to stop this for a moment. And then I can enable materialized views, specify a key for the materialized views, and I have a column here that I'm going to use as a key, and add a query. So here I'm going to put CPU usage, and select all the columns that I want in my materialized view, right? And then save changes. So when I create this, it creates a REST endpoint, which will provide access to that materialized view to other applications. So now if I start my query, the query is still going to be writing into that Kafka topic here, which hopefully, yeah, is here. And I can see the data that I'm writing to it right now, which is those aggregations that I'm doing. But now I'm also making this data available through a REST endpoint. So I can actually connect to that REST endpoint and see the data here. So now I can use this for a number of other things, right? It opens a lot of possibilities. For example, if I have a notebook, if you're using Jupyter or any kind of notebook in your application, I can connect directly to that REST endpoint from the notebook. Let me create a session here in my notebook, a Python session, and I can start manipulating that in like doing exploration in that data using machine learning or anything that I can do in the notebook, right? So if I do import pandas SPD, I hope I get this right. So I'm going to load the data frame from using read JSON from pandas. And here, let me increase this a little bit. Yep. And here, what I want is just the copy this URL and paste it here. So if I run this, it loaded my data frame. I can visualize my data frame here. So this is the content of the materialized view that it just retrieved there. And I can start doing other things. I can do sort values by, let's say, timestamp, plot x equal to times, oops, timestamp y equal to CPU. If I execute this, yeah, I have like a CPU chart here of what's happening on my notebook as we speak in real time, right? I can also,
Andre,
just
to keep track of time, just have a few minutes, and I wanted to cover some of the great questions that we have as well. Sorry about that.
I'm just finishing here. Give me 2 minutes.
Sure.
So that materialized view that I'm writing here, that I was accessing from my notebook here, can also be accessed by other systems like Grafana, for example, right? So I would, yeah. So you could have you could be using SSB to do all the heavy lifting and analytics and computations on data that you're streaming from different types of sources. and making that available in different formats in different locations for downstream applications that you need to feed. That could be BI applications, other streaming applications that you have downstreams, dashboards, etc. Like I have a Grafana example here, but again, like I would have to modify this to, let me just see here, to work with my latest one. Not sure. Yeah. So for example, here is a Grafana example, reading exactly from that same materialized view in real time. So every 5 seconds, it also updates with the latest state and what's happening on my computer here. So it's just to give you an idea of how powerful this is. And you could do a lot more with this. Like you have templates, as I mentioned, to write to a number of different other locations or read from a number of different other locations. And you can mix streaming data with batch data, which is an awesome thing to do to enable streaming processing and enrichment in the way that we just saw here. Okay, so without further ado, let's go to the questions. I want to make sure that we cover some of those, so we're already over time, but we can spend a few more minutes covering the questions here.
Yeah, that was beautiful, Andre. Thanks so much. I know you're so passionate about this, right? So we have already gone 2 minutes over time, but quickly going over some of the great questions, right? So the first one that we have is from Win in Australia, from YouTube, and his question is, what's the performance impact of reading continuously from relational databases and using relational databases as a sink? So I guess his question is more about how do you do CDC or continuous data capture using Flink, and what kind of performance impact it would have as a source or a sink on the database. I think there's a small glitch. Andre, we've lost your voice. Let me just, Prila, can you bring Andre onto the front screen? Apologies, this is, there's a technical glitch over here, so we have lost Andre, but he's not live as well. Yeah, so let me take a couple of questions myself. So I think the question is more about the performance impact on the relational databases. So definitely, these kind of streaming technologies are meant for streaming sources and things like Kafka and message queues and things like that, right? For databases itself, if you have extremely high throughput and low latency requirements, then relational databases is not the right tool for change data capture and also as a source and a sink. You typically would want to have some kind of an in-memory database or some kind of a NoSQL database as a sink if you want to persist these kind of streaming data for low latency requirements. but relational databases would definitely be bogged down with these kind of low latency, low streaming engine kind of things. Right? I hope that answers your question, Win.
Yeah, can I add one more thing to that?
Okay,
Can you guys
Andre, we
hear me?
have you back. Yeah, go ahead.
Yeah, so, and I was talking about this before, but I don't know if you guys missed everything I said. But
Yeah, I think we missed all of everything you said.
yeah, I think like when you mention reading continuously from a relational database, I mean like you're reading from a streaming source and then doing lookups, continuously doing lookups on the relational database to enrich your stream, right? So in that sense, you're continuously going back to the relational database to read data, and your concern is valid. Like you could like make performance, like create performance problems on that database if you're doing that at very high volumes. So depending on the volumes that you're considering here, you might want to consider systems that have the capacity to absorb that very high number of lookups. Instead of a relational database, for example, use a HBase source or a Kudu source that can do lookups at very high volumes very quickly. Or alternatively, you could, if you're creating a Flink job from scratch, you could look at using state to store some of that data instead of going to an external database to do that.
Yep. Thanks, Andre. Another question that we have is from Indresh Yadav on LinkedIn. He's asking what kind of servers are needed to run Flink on. I mean, what kind of hardware specs is really required?
We have specific hardware specs on our website that you can look up, but it's not something special. Flink can make good use of memory, and if your application is a stateful application and you're writing a lot of state to disk, it can benefit from having SSD disks that have like faster throughputs than the spinning disks in there. But those nodes are not special. Flink scales horizontally rather than vertically. So if you need a lot of performance, if you need to scale the amount of data that you're processing, you'd rather add more nodes to your Flink cluster than like buy like very expensive beefy nodes there. And that would also provide you better fault tolerance. And like if you lose a node, you still have other nodes that can continue the processing without much impact.
Cool. Yeah. So I think, but all the servers can be commodity servers, right? You don't really need like super beefy ones. I guess maybe like 8-core, 32 gigs of RAM, and few SSDs and stuff would be more than enough.
Yeah, absolutely.
Okay. Cool. The next question is from MC Cat on YouTube. Does Flink have a cache that it maintains and waits for missing data while it waits for missing data? For example, if I need to batch an event with certain sequence and certain size, is it possible to do in Flink? I guess this question is more about how do we cache data within Flink?
Yes. Yep. Flink has that capability, and it's built in within the API. You can make use of that both in a Flink Java job if you implement your job, but in SSB you can also define what we call the watermark there, which is like a window of time that Flink waits for events that are out of order to arrive before you actually process window aggregation, right? So for example, if you're computing averages or doing any calculation on windows of 1 minute, but you know that your data is out of order and you might have some data that's delayed by, let's say, at most 30 seconds, you can define in your job that the job should wait those 30 seconds so that it's sure that it's collected all the data and got all the data that was out of order before it actually completes that aggregation window and emits the output, right? So yeah, so the answer is yes, Flink has full support to that, both in the API directly, but you can also do that in SSB without having to use Java for that.
Cool. And a follow-up question typically is, how big can these windows be, right? So, for example, I need to do a window of maybe a month or maybe 6 months or so. How do we do that? And do we really require in-memory, huge amounts of RAM and stuff like that? Or how is it?
The large windows come down to, so as you're computing, doing computations on a window, the intermediate results of those computations are stored in your job state within Flink, right? So the larger the windows, the more state it's going to have to store, right? So as I said, Flink stores the state in memory, but it can also offload state to the local disk to maintain the fast access there. But as your applications grow, you're going to have, as your windows grow, your applications are going to have more and more state to store, right? So you have to be aware of the amount of memory that your jobs are running, like your JVMs cannot run out of memory, and your disks on your servers also cannot run out of space to store that state. Like we have customers who run applications that have terabytes of state distributed across the cluster, right? So the larger your windows are and the larger your estate is, you need to make sure that you increase the parallelism. You add more nodes to your cluster to support the storage of that state or of the keeping of that state. So in that regard, I don't see a limit on the size of the windows. If you want a window of 1 year, you can do it as long as you size your cluster accordingly to be able to support that with good performance.
Yeah. There are many beautiful and awesome questions, right? But we are running out of time, and just a couple of more minutes and we decide the winner of the prize as well. Let's just take one more, Andre, if you don't mind. This is from Kumar Shambhavam on LinkedIn, and he asks, should I learn Apache Flume? And what's the best alternative to Apache Flume? If not?
Apache Flume?
Yeah, Flume.
Well, my personal my personal opinion is no, you should not. Like Flume is a outdated technology. Like Cloudera doesn't even support that anymore. We have deprecated that from our platform, and there is a number of other technologies that can replace Flume and doing a lot and run a lot more efficiently than Flume. Our direct replacement for Flume right now in the platform is Apache NiFi, which can do pretty much what Flume used to do and a lot more. So unless you have a very specific reason for wanting to learn Flume, I would say no, probably you're looking at the wrong technology.
Yeah, absolutely. I think that leads us to a great other topic that I was thinking of now. Maybe we should have an Apache NiFi 101 for all the folks who don't know about that technology as a follow-up meetup topic as well. And we'll have Andre back on that as well. I think we're running out of time. So Andre, maybe...
Let's do the last question and we wrap up.
No, we still need to decide the winner. So maybe let me do this. I really like the question of reading and writing to databases and what the performance impact of that was. So I think WinFan is the one who asked that question. So Win, if you're still around, you could please email your personal address to our backstage staff, Ramon. His email address is rchow, rchow @cloudera.com. That's again rchow @cloudera.com. And you should receive these swags pretty soon on your address. Congratulations again, Win. Anyway, then I think we're out of time now. We'll have super exciting sessions again, follow up to these sessions again. We have a number of different speakers lined up to share a lot of information as well. if you have some great ideas that you want to hear about open source technologies, what Cloudera is doing, do let us know as well on the chat on YouTube or LinkedIn, and we'll try our best to address those topics as well. Thanks, Andre. Thanks again to the Backstage staff, and thanks everyone for joining in and so much giving so much of your time and listening us out. Hope to see you again on the next one then. Thank you so much.
Thank you, Saurabh. Thank you, Freela
Thanks.
and Ramon.
Thanks, everybody.
Thank
Bye.
everyone for attending this session today.